Okay, let's dive into this. Welcome back, focus learners, to today's explainer. Now, if you're gearing up for your college algebra finals, you already know that Lecture 16 can be, well, a bit of a hurdle. It's the kind of chapter that honestly might make you want to toss your textbook right out the window. But hold on, don't do that just yet. Today, our single laser-focused goal is completely demystifying these probability concepts step by step. We are absolutely going to turn that exam anxiety into total confidence. Here is the roadmap for our bootcamp. We're covering the core essentials. First, foundations, coins and dice. Second, permutations, the statistics problem. Third, combinations, players and bulbs. Fourth, the committee conundrum. Fifth, mutually exclusive events. And finally, number 6, independent events. All right, let's conquer this. Starting with Section 1, foundations, coins and dice. Before we can do any complex math, we literally must define our universe. Everything in probability has to start from understanding exactly what's possible. What's really fascinating here is just how simple the core foundation actually is. The mathematical formula for probability, it's just your favorable chances divided by your total chances. Now, that total chances part, that's what we call your sample space. Simply put, it's a set consisting of all possible outcomes of an experiment. It's your total universe, like the numbers 1 through 6 when you're tossing a single die. In an event, well, that's just a subset of that sample space. It's your specific target, like, say, wanting to roll an even number. Let's put this into practice right away. Imagine 2 coins are tossed together. First things first, we define our universe, our sample space. You could get heads heads, heads tails, tails heads, or tails tails. So that's 4 total outcomes, right? Now, what's the probability of getting the same faces? Well, looking at our little universe, only heads heads and tails tails fit the bill. That's 2 favorable chances out of 4 total, which simplifies perfectly to 1/2. What about getting at least 1 head? That covers heads heads, heads tails, and tails heads. That's 3 favorable chances out of 4, so 3/4. And different faces. That's just heads tails and tails heads, giving us 2 out of 4, or a 1/2 probability. See? It's just step-by-step logic. Okay, let's step it up to 2 dice. We're going to use what I like to call the comforting 3-step attack. Step 1, identify the total sample space. Since each die has 6 faces, 2 dice give us 6 times 6, which is 36 total possible combinations. Step 2, find your favorable outcomes. Say we want to find the probability that the sum of the dice is exactly 10. We just systematically list the combinations that work. We've got a 4 and a 6, a 5 and a 5, and a 6 and a 4. That is exactly 3 favorable outcomes. And step 3, just divide the favorable by the total. And this brilliantly illustrates our first real bootcamp victory. We take our 3 favorable outcomes, divide by our 36 total outcomes, and we get 3/36. That simplifies perfectly down to 1/12. Look at that. You've just conquered the foundational logic. Moving on to Section 2, permutations, the statistics problem. We're transitioning to our advanced tools now. We are moving from simple coins and dice to a classic scrambling problem, one where the order of the items absolutely matters. Here's a super classic exam question. The letters of the word statistics are scrambled. What is the probability that the vowels come together, or that the consonants do not occur together? Now, I know word permutation questions can seem kind of tricky because of repeating letters. So the absolute crucial point here is to handle this systematically using a grouping strategy. Let's walk through the math step by step. First, we find our total universe. The word statistics has 10 letters, so we start with 10 factorial. But wait, hold on. We have repeating letters. 3 S's, 3 T's, and 2 I's. We absolutely must divide 10 factorial by 3 factorial times 3 factorial times 2 factorial to get our true total sample space. Next, to find the favorable chances where vowels actually come together, we use what's called the block method. We take the vowels A, I, and essentially tape them together into one single block. Now we're arranging 7 consonants plus 1 vowel block. That equals 8 items to arrange, so 8 factorial divided by our repeating consonants. But remember, and this is a big catch, the vowels can swap places inside their own little block. So we multiply that by the arrangements of the vowels, which is 3 factorial divided by the 2 repeating I's. Just divide that favorable number by your total sample space, and boom, you have your probability. All right, Section 3, combinations, players, and bulbs. We just conquered permutations where order matters, so this signals a shift in logic to where the order of selection doesn't matter at all, kind of like picking a team.
Imagine you're selecting 11 players out of a 16-player roster. The total sample space is simple enough: 16 choose 11. But what if the exam asks for the probability that a team includes a particular star player? Here's the logic. That one star player is locked in. That means one roster spot is taken, and one player is removed from the available pool. So your favorable chance is choosing the remaining 10 spots from the remaining 15 players. So 15 choose 10. Conversely, if you must exclude a particular player, you ban them from the pool entirely. Now you only have 15 players to choose from, but you still have to fill all 11 spots. So in that case, your favorable chances are 15 choose 11. Just divide either of those by the total 16 choose 11, and you've solved it.
Okay, here's another combination conundrum that honestly trips up a lot of students. From a collection of 10 light bulbs, where 4 are good and 6 are fuses, meaning they're duds, 3 are selected at random and put into a socket. What is the probability that there will be light? Now, this phrasing is a bit of a trap. Saying there will be light is just a tricky, sneaky way of saying you need at least one good bulb. Let's demystify this at least one shortcut. Step 1. Your total sample space is choosing 3 bulbs from 10, so 10 choose 3. Now, sure, you could calculate the exact probability of picking exactly 1 good bulb, then 2 good bulbs, then 3 good bulbs, and painfully add them all up. But actually, it's mathematically way faster to find the exact opposite. Ask yourself, what is the probability of picking all duds? We have 6 fuse bulbs, so picking 3 duds is 6 choose 3. You find that probability, 6 choose 3 divided by 10 choose 3, and simply subtract it from 1. 1 minus the probability of total darkness practically guarantees the probability of light. How cool is that?
Section 4, the committee conundrum. You guys are doing a fantastic job so far. Now, take a deep breath, because we're introducing some of the heavy lifting combinatorics.
Let's say we have a club with 7 men and 4 women, and we need to form a 5-member committee. Our total universe is 11 people, choosing 5, so 11 choose 5. If the exam asks for exactly 4 men, your favorable outcome is choosing 4 men from the 7, which is 7 choose 4, and you multiply that by choosing 1 woman from the 4, which is 4 choose 1, to finish out the 5-person committee. But you really need to watch out for phrases like at least and at most. For example, at least 2 women means calculating the exact combinations for 2 women and 3 men, plus 3 women and 2 men, plus 4 women and 1 man. You calculate those 3 exact scenarios separately, add the results all together, and divide by your total sample space. It's not actually hard, it just requires some systematic patience.
Moving into Section 5, mutually exclusive events. Let's shift gears here from counting groups to actually combining probability rules. Mutually exclusive simply means 2 events have absolutely 0 points in common. They physically cannot happen at the same time. Think about it. If you throw a single die, getting an even number and getting an odd number are mutually exclusive. It's literally impossible to do both on just one roll. But drawing a heart and drawing a queen from a deck of cards, those are non-mutually exclusive. Why? Well, because the Queen of Hearts exists. There is a distinct overlap. Let's see how this builds perfectly into our next big formula, the sum principle of probability. If you want to find the probability of drawing a heart or a queen, you use the formula. Probability of A plus probability of B minus the overlapping probability of A and B. So the probability of drawing a heart is 13 out of 52. The probability of drawing a queen is 4 out of 52. If we just add them up, we've double counted the Queen of Hearts, so we have to subtract that 1 out of 52 overlap. 13 plus 4 minus 1 equals 16. The probability is 16 out of 52. It's just easy addition and subtraction once you know the rule. Section 6, independent events. We have officially arrived at the final mathematical hurdle of the lecture. This is where one action couldn't care less about the other. By definition, independent events are when the occurrence of one event does not affect the probability of the other. For example, tossing a coin and throwing a die. The coin doesn't magically know what the die is doing, right? The rule here is incredibly simple. When independent events occur together, you just multiply their individual probabilities. The probability of getting a head is 1/2. The probability of rolling a 6 is 1/6. You want a head and a 6? Just multiply 1/2 by 1/6 and you get 1/12. Let's apply this to a final class activity. Say Habib has a 1/4 chance of solving a math sum, which means he naturally has a 3/4 chance of failing. Taha has a 1/5 chance of solving it, meaning a 4/5 chance of failing. If they both try, what's the probability that both solve it? Because they're independent, we just multiply their success fractions. 1/4 times 1/5 equals 1/20. What is the probability neither solves it? Just multiply their failure fractions. 3/4 times 4/5 equals 12/20. And what about either one solving it? We use our sum principle from earlier. Probability of Habib solving it, which is 1/4, plus the probability of Taha, which is 1/5, minus the probability they both solve it, which is 1/20. Do the fraction math and you get 8/20, which simplifies down to 2/5. Wow, you just solved a complex multi-step word problem entirely in your head.
And that, my friends, brings us to the end of our boot camp. We have systematically tackled coins, tricky permutations, combinations, and all the core probability rules from Lecture 16. Remember, probability isn't magic. It is just structured logic. So I leave you with this final provocative thought. Will you clearly define your universe, step back, and systematically find your favorable chances on the final exam? Honestly, I am absolutely confident that you will. Keep practicing, trust the process, and you are going to absolutely crush this.